Welcome to the problem walkthrough for 3 Divisors 2. In this session, we'll explore an interesting mathematical problem, break it down step by step, and identify the best approach to solve it effectively. Let's dive in and get started. In this problem, you are given a positive integer n, and your task is to determine how many positive integers less than or equal to n have exactly 3 positive divisors. To better understand this, recall that a positive integer x has exactly 3 divisors if and only if it can be expressed as the square of a prime number. For example, if x equals p squared, where p is a prime, then the divisors of x are 1, p, and x itself, which totals to exactly 3. This means that the number must not only be a perfect square but also have a square root that is a prime number. The input to the problem is a single integer n, which falls within the range of 1 to 10 to the power of 9. And the output is a single integer representing the count of such numbers. Let's examine some examples to clarify the concept. For the first example, if the input is n equals 10, the output is 2. Here's why: the numbers less than or equal to 10 that have exactly 3 divisors are 4 and 9. The number 4 has divisors 1, 2, and 4, while 9 has divisors 1, 3, and 9. Both of these numbers are the squares of prime numbers, specifically, 4 equals 2 squared, and 9 equals 3 squared. Since there are 2 such numbers, the output is 2. In the second example, if n equals 30, the output is 3. This is because the numbers 4, 9, and 25 all have exactly 3 divisors. The reasoning is similar: 4 is 2 squared, 9 is 3 squared, and 25 is 5 squared. Thus, the count is 3. Continuing with the second example, we can see that the explanation holds true for all numbers less than or equal to 30 that have exactly 3 divisors. Each of these numbers, 4, 9, and 25, satisfies the condition of being the square of a prime number. For a final example, consider n equals 1. In this case, the output is 0 because there are no numbers less than or equal to 1 that fit the criteria of having exactly 3 divisors. Hence, the output is 0. These examples illustrate how the problem is solved by identifying numbers that are squares of primes within the given range. To summarize, the constraints for this problem are that n can range from 1 to 10 to the power of 9. It's important to note that a number with exactly 3 divisors must be the square of a prime number. To solve the problem efficiently, you only need to identify all prime numbers less than or equal to the square root of n. Their squares will be the only numbers with exactly 3 divisors that are less than or equal to n. Be mindful of edge cases such as very small values of n, like 1 or 2, extremely large values close to 10 to the power of 9, cases where n is not a perfect square, and cases where n is exactly the square of a prime number. These considerations will help ensure your solution is both correct and efficient. To solve this problem, we need to identify how many integers less than or equal to n have exactly 3 divisors. The key mathematical insight is that a number x has exactly 3 divisors if and only if it can be expressed as p squared, where p is a prime number. This is because the divisors of p squared are exactly 1, p squared, which gives us 3 divisors. So, our goal simplifies to finding all prime numbers p such that p squared is less than or equal to n. Once we have this list of primes, we can directly count how many of their squares satisfy this condition. One way to approach the problem is through a brute force method. The intuition here is to iterate through all numbers from 1 to n and, for each number, count its divisors. If a number has exactly 3 divisors, we increment our count. To break this down, we would loop through every number from 1 to n, and for each number, calculate its divisors. This divisor counting for a single number takes sqrt k time, as we only need to check up to the square root of the number. However, since we are doing this for all numbers up to n, the overall complexity becomes n asterisk sqrt n. While this method is straightforward and easy to understand, it becomes inefficient for large values of n due to the nested iterations involved. A more efficient solution involves optimizing the approach by focusing on prime numbers. The intuition here is that only the squares of prime numbers can have exactly 3 divisors. To implement this, we use the sieve of Eratosthenes to efficiently generate all prime numbers up to the square root of n. Once we have the primes, we simply check for each prime p whether p squared is less than or equal to n. If it is, we count it as a valid number. The sieve of Eratosthenes itself runs in O, n log n, time for generating primes up to sqrt, n, and the subsequent checks are completed in O, sqrt, n. This results in an overall complexity of O, sqrt, n, asterisk log n. By focusing on primes and their squares, we eliminate unnecessary computations, making this approach much faster for larger values of n. This is why we chose the optimized method for solving the problem. It leverages the mathematical insight about prime squares to significantly reduce the computational workload. When comparing the two approaches, the brute force method has the advantage of being simple to implement and easy to understand. However, its O, n asterisk sqrt, n, time complexity makes it unsuitable for large values of n, as it involves nested iterations for divisor counting. On the other hand, the optimized approach, which uses the sieve of Eratosthenes, is much more efficient for large inputs. By focusing only on generating primes and checking their squares, it drastically reduces the number of computations. While the sieve algorithm might be slightly more complex to implement, its efficiency far outweighs this drawback. Overall, the optimized approach is the best choice for this problem, as it balances efficiency with correctness, ensuring the solution remains computationally feasible even for large values of n. To solve the problem of finding how many integers less than or equal to n have exactly 3 divisors, we start by understanding the mathematical property behind such numbers. A number has exactly 3 divisors if and only if it can be expressed as p squared, where p is a prime number. This is because the divisors of p squared are precisely 1, p squared, with no additional divisors. For example, 4, which is 2 squared, has the divisors 1, 2, 4, while 9, which is 3 squared, has the divisors 1, 3, 9. The key insight here is that we only need to find the prime numbers p where p squared is less than or equal to n. To do this efficiently, we used the sieve of Eratosthenes to generate all prime numbers up to the square root of n. This approach is efficient because if p squared exceeds n, then p cannot contribute to the result. For instance, if n is 30, we only need prime numbers up to approximately 5.48, which are 2, 3, 5. The squares of these primes 4, 9, and 25 are the only numbers less than or equal to 30 with exactly 3 divisors. Next, we focus on counting the valid squares of primes. For each prime number p generated by the sieve, we calculate p squared. If p squared is less than or equal to n, we include it in our count. As soon as p squared exceeds n, we stop, since any further primes will also have squares larger than n. The final count of such numbers gives us the desired result. This approach is highly efficient because it leverages the mathematical property that only perfect squares of primes can satisfy the condition of having exactly 3 divisors. The sieve of Eratosthenes ensures that we generate primes up to the square root of n efficiently, avoiding the need for trial division for every number up to n. By stopping the sieve at the square root of n and focusing only on p squared values, we minimize unnecessary computations. The sieve itself operates with a time complexity of O, m log m, where m is the square root of n, making it scalable even for large values of n. To implement this algorithm, we rely on specific data structures to ensure efficiency. First, a Boolean array is used for the sieve of Eratosthenes. This array, of size equal to the square root of n, is used to mark whether each number is prime. It enables us to generate primes efficiently by marking multiples of each prime as non-prime. Additionally, a list is used to store the prime numbers generated by the sieve. This list simplifies the iteration process when calculating p squared for each prime. Considering edge cases, for values of n less than 4, the result is always 0 because there are no squares of primes within this range. For larger values of n, the algorithm remains efficient due to its logarithmic factors and the restriction of prime checks to the square root of n. Finally, non-prime squares are automatically excluded because the algorithm only considers squares of numbers identified as prime through the sieve. Analyzing the algorithm's complexity, the time complexity of the sieve is O, sqrt, n, log sqrt, n. This accounts for marking multiples of primes as non-prime up to the square root of n. Iterating over the primes to compute their squares adds another O, pi, sqrt, n, complexity, where pi, x, represents the number of primes up to x. Together, these components make the algorithm highly efficient. The space complexity is O, sqrt, n, due to the Boolean array used for the sieve. Let's now take a closer look at the implementation. First, the algorithm checks if n is less than 4, immediately returning 0 if true. Then, it calculates the square root of n and initializes the sieve as a Boolean array. The sieve begins by marking 0 and 1 as non-prime and proceeds to mark multiples of each discovered prime as non-prime. This allows us to efficiently generate all primes up to the square root of n. After generating the primes, we store them in a list for easy iteration. We then initialize a count variable to 0 and iterate through the list of primes. For each prime p, we calculate p squared. If p squared is less than or equal to n, we increment the count. If p squared exceeds n, we break out of the loop, as no further primes can contribute to the result. Finally, we return the count. For example, if n is 30, the algorithm identifies the primes up to the square root of 30 as 2, 3, 5. Their squares, 4, 9, and 25, are counted, resulting in an output of 3. This implementation demonstrates the efficiency and clarity of the algorithm. By focusing on the mathematical properties of numbers with exactly 3 divisors and leveraging the sieve of Eratosthenes, we achieve a solution that is both optimal and easy to understand. This implementation solves the problem of finding how many integers less than or equal to n have exactly 3 divisors. Here's how it works. 1. Understanding the problem. A number has exactly 3 divisors if and only if it can be expressed as p squared, where p is a prime number. For example, 4 equals 2 squared, and its divisors are 1, 2, 4, hence, it has 3 divisors. 2. Helper function. A nested helper function is _prime is defined to check if a number is prime. It works by iterating from 2 to the square root of the number, checking divisibility. If any divisor is found, the number is not prime. 3. Iterating over possible prime bases. The algorithm iterates over integers from 2 to the square root of n. Only values that are prime are considered as potential bases p for p squared. For checking the square, for each prime p, the algorithm checks if p squared is less than or equal to n. If so, the count is increment. 5. Returning the count. Finally, the count of numbers with exactly 3 divisors is returned. The overall complexity of this solution is efficient due to the prime checking optimization and the limited range of iteration, up to the square root of n. Here, we begin our Java implementation for solving the problem of finding numbers with exactly 3 divisors. First, we import the math library, which will help us with mathematical operations like square root calculation. Then, we define a helper method called isPrime to determine if a given number is prime. This method returns false for numbers less than 2, as they are not prime. For numbers 2 or greater, it checks divisibility from 2 up to the square root of the number. If any number in this range evenly divides x, it is not prime, and the method returns false. Otherwise, it returns true, confirming the number is prime. Next, we define the main method, 3divisors, which takes an integer n as input and initializes a variable count to 0. This variable will keep track of numbers with exactly 3 divisors. We then iterate from 2 up to the square root of n. The primary idea here is that a number has exactly 3 divisors if it is the square of a prime number. So, within this loop, we check if I is a prime number using our helper method. If it is, we further ensure that squaring I does not exceed n. This check for overflow is done using a cast to long. If both conditions are met, we increment the count. Finally, after the loop completes, we return the value of count. This represents the total number of integers less than or equal to n that have exactly 3 divisors. The implementation is efficient because we limit our checks to numbers up to the square root of n, significantly reducing the number of computations. Additionally, the helper method ensures that we only consider prime numbers, which is critical for identifying numbers with exactly 3 divisors. The solution is both concise and optimized for the problem constraints. In this problem, we are tasked with determining how many numbers up to a given integer n have exactly 3 divisors. A number has exactly 3 divisors if and only if it is the square of a prime number. For example, 4, which is the square of 2, and 9, which is the square of 3, each have exactly 3 divisors, 1, the number itself, and its square root. On the other hand, a number like 6 doesn't work because it has more than 3 divisors.
To illustrate, consider the example where n equals 10.
We initialize a count variable to 0, which will keep track of the numbers with 3 divisors. Then, we iterate over integers I from 2 up to the square root of n, rounded down. In this case, the square root of 10 is approximately 3.16, so I takes on the values 2 and 3. For the first iteration, where I equals 2, we check if 2 is a prime number using the helper function is_prime. Since 2 is greater than 1 and has no divisors other than 1 and itself, it is a prime number. Next, we check whether the square of 2, which is 4, is less than or equal to 10.
Since it is, we increment the count to 1. Now, in the second iteration, where I equals 3, we again check if 3 is a prime number. As with 2, 3 is greater than 1 and has no divisors other than 1 and itself, so it is also a prime number. We then check whether the square of 3, which is 9, is less than or equal to 10. Since this condition is satisfied, we increment the count to 2. At the end of this process, we return the count, which is 2, as the numbers with exactly 3 divisors in this range are 4 and 9. Now, let's consider a second example where n equals 25. Here, we initialize the count to 0 again and iterate I from 2 to the square root of 25, which is 5. For the first iteration, where I is 2, we confirm that 2 is prime using the is_prime function. Since the square of 2, which is 4, is less than or equal to 25, we increase the count to 1. In the next iteration, where I equals 3, we check if 3 is prime. It is, and since the square of 3, which is 9, is also less than or equal to 25, we increment the count to 2. For I equal to 4, we check if 4 is a prime number. Since 4 is divisible by 2, it is not a prime number, so we skip this iteration without making any changes to the count. In the final iteration for this example, where I equals 5, we determine that 5 is a prime number. Since the square of 5, which is 25, is equal to n, it satisfies the condition, and we increase the count to 3. After completing all iterations, the final count is 3, corresponding to the numbers 4, 9, and 25, which each have exactly 3 divisors. Moving on to a larger example, let's take n equal to 50. Here, the process is similar. We initialize the count to 0 and iterate I from 2 to the square root of 50, which is approximately 7. For I equal to 2, we determine it is prime, and its square, 4, is less than or equal to 50, so the count becomes 1. For I equal to 3, we find that 3 is prime, and its square, 9, is also less than or equal to 50, increasing the count to 2. For the next few iterations, we continue checking numbers. When I equals 4, it is not a prime number, so we skip it. For I equal to 5, it is a prime number, and its square, 25, satisfies the condition, so the count increases to 3. When I equals 6, it is not prime, so we skip it. Finally, for I equal to 7, we confirm that it is prime, and its square, 49, is less than or equal to 50, increasing the count to 4. At the end of this process, the count is 4, and the numbers with exactly 3 divisors are 4, 9, 25, and 49. This concludes our solution, demonstrating how we determine the count of numbers with 3 divisors up to any given n. To analyze the time complexity of this algorithm, we need to break it into its main steps. First, consider the outer loop, which iterates through all integers from 2 up to the square root of n. Since the upper bound of this range is approximately sqrt, n, the number of iterations in this loop is proportional to O, sqrt, n. Next, for each integer I, we check whether I is a prime number using the is_prime function. This function itself involves iterating through numbers from 2 to the square root of I, requiring up to O, sqrt, I, operations. When we combine these, the total cost of all primality checks can be approximated by summing sqrt, I, for every I between 2 and sqrt, n. Using mathematical approximations for this summation, the total cost evaluates to about O, n caret, 3/4. This means the primality checking step dominates the time complexity of the algorithm. Now, let's factor in the final condition, where the algorithm checks whether I** is less than or equal to n. For every valid I that is a prime number, this check is performed. Since it's a simple comparison, it operates in constant time for each iteration. Over all iterations, this contributes an additional O, sqrt, n, to the time complexity.
When we combine all these steps, the dominant term is the cost of the primality checks, which is O(n)(3/4). Hence, the overall time complexity of the algorithm is O(n)(3/4). Moving to space complexity, the algorithm is efficient because it uses only a constant amount of extra space. Variables like count and temporary variables within the is_prime function do not scale with the size of the input. Since no additional data structures or recursion are used, the space complexity remains constant at O(1). The overall space complexity is therefore O(1), as the algorithm operates entirely within constant space. To appreciate the efficiency of this approach, let's compare it to a naive solution. A naive method would involve iterating through all numbers from 1 to n and counting divisors for each. This process requires n iterations, with each iteration taking n time to count divisors. Consequently, the time complexity of the naive approach is n*(n), which is far worse than the optimized algorithm. In contrast, the current approach leverages the property that numbers with exactly 3 divisors are squares of primes. By focusing only on prime numbers and avoiding unnecessary calculations for non-primes, the algorithm significantly reduces computational overhead, achieving an optimized time complexity of O(n)(3/4). To understand the performance further, let's analyze the best, average, and worst cases. In the best case, when n is small, there are very few numbers in the range from 2 to n. While the algorithm still performs primality checks, the overall cost remains proportional to O(n)(3/4). For the average case, most typical inputs will have a reasonable number of numbers to check within this range. Again, the cost is dominated by the primality checks, maintaining the complexity at O(n)(3/4). Even in the worst case, for the largest possible value of n, the algorithm scales predictably, as the primality checks remain the most expensive operation. This ensures the algorithm's time complexity does not exceed O(n)(3/4) in any scenario. When solving this problem, there are a few common mistakes you should watch out for. First, it's important not to confuse prime numbers with composite numbers. While prime numbers have exactly 2 divisors, a number with exactly 3 divisors must be the square of a prime. For example, 4, which is 2 squared, and 9, which is 3 squared, both meet this condition. Second, iterating over all numbers up to n to check for 3 divisors is inefficient. This property only applies to squares of primes, so focusing directly on primes saves unnecessary effort. Lastly, an inefficient prime checking method, like using trial division for every number, can slow your solution drastically. Instead, pre-computing primes up to the square root of n using the sieve of Eratosthenes is a much faster approach and is computationally efficient at n log n. Another mistake to avoid is ignoring edge cases. For example, when n is less than 4, no numbers exist that have exactly 3 divisors, as the smallest prime square is 4, which is 2 squared. Your solution should handle these small inputs gracefully. Additionally, off-by-1 errors are a common pitfall. When determining the range of numbers to include, it's easy to miscalculate and either exclude n or go beyond it accidentally. Make sure the less than or equal to n condition is properly implemented and double-check your loop boundaries to avoid errors in your final results. Understanding the deeper mathematical insight behind this problem is key. Here, the relationship between primes and their squares is fundamental. Only the squares of prime numbers have exactly 3 divisors, so the focus should be on identifying primes efficiently. The sieve of Eratosthenes is highly effective for pre-computing all primes up to the square root of n, and from there, you can count their squares that are less than or equal to n. This optimized approach reduces the complexity to n log n. In an interview setting, recognizing the prime square property and explaining it clearly demonstrates strong mathematical and problem-solving skills. Be prepared to discuss edge cases such as small values of n, large inputs, and the trade-offs in computational efficiency. To strengthen your understanding and practice similar concepts, you can explore related problems. For instance, LeetCode 204, Count Primes, is a great way to refine your knowledge of the sieve of Eratosthenes and prime counting techniques. LeetCode 507, Perfect Number, delves into the concept of divisors in a different context, which can help broaden your divisor-related problem-solving skills. Additionally, LeetCode 263, ugly number, involves divisors and prime factorization, offering another perspective on working with primes. While LeetCode 1328, break a palindrome, is not directly related, it challenges you to efficiently handle constraints and edge cases, a skill that's just as important for this problem. Finally, let's consider some alternative approaches to the problem. A brute force solution involves iterating through all numbers up to n, counting their divisors, and checking if exactly 3 exist. While simple to implement, this approach is inefficient with a complexity of O, n *sqrt, n, making it suitable only for small values of n. A more optimized approach is to use a sieve to find all primes up to the square root of n and then count their squares that are less than or equal to n. This method is significantly faster and scalable for larger inputs but requires a solid understanding of the sieve of Eratosthenes. For scenarios involving multiple queries, pre-computing results for all numbers with exactly 3 divisors up to a maximum n can be beneficial. While this is faster for repeated queries, it requires additional memory to store the pre-computed data. Each of these methods has its trade-offs, and the choice depends on the specific constraints and requirements of the problem.
Great job!
In this walkthrough, we explored how to efficiently solve the 3 divisors 2 problem by focusing on mathematical properties and reducing computational overhead. Remember, practice makes perfect, so keep challenging yourself with similar problems.
Thanks for tuning in, and see you in the next one. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!